Recording is rolling, 7th period on Monday, October 4th. Yeah, welcome back from the weekend. I have a new couple pages for you guys. Do you guys see a clip to the right side of your desk? Some papers look like this, like stapled together. Does anybody not have this? Anybody not have this? All right. So one of these pages is some problems from chapter 6. You might remember chapter 6 from your book. There were some projectiles. I left those off. Just focus on the centripetal force questions, like your guys' lab from last week. Then there's some chapter 7 questions on gravitation. The way we're going to go through the next couple weeks, it's going to look kind of like this is somewhat of a roadmap. We'll talk about some centripetal force. By the end of class today, I'll get you guys started on universal gravitation. We're eventually going to bring these two ideas together and talk about orbits and things like that. You know what I think was a good idea last time, and we'll try this again and maybe keep doing this, keep working, is I've got a main homework for you guys that almost certainly cover all these problems or almost all these problems in class. And then there'll be this bonus homework that if you don't do it, it's not going to hurt you, but if you do it, then I'll give you guys some extra points in the grade book. There are picture retakes tomorrow, if that was relevant to you. Got that? And quizzes. So we pulled the top scientist list. Here we go. Top scientist list for forces. Graded these over the weekend. You guys did really awesome overall, especially if your name is up there. If your name is up there, you did super awesome. I do want to, of course, get these back to you guys as soon as I can. I'm still waiting on just a few more late quizzes to come in, so waiting on those. Then once I get them all in, then we'll post the solutions, get these back to you guys. And then we'll also do the same thing that we did last couple, which is if you want to write corrections for any problems that you missed and turn them into corrections, then I'll give you guys a partial credit back. All right, so any questions so far? All right, let's dive into this starter question. What is the tangential speed of this puck on the air hockey table? Say this one right here. In order to maintain dynamic equilibrium? Now remember what that phrase means too. So equilibrium, you guys know equilibrium, like static equilibrium means that all the forces cancel out. Like this weight hanging down here, this 3 kilogram mass. It has a weight pulling down, it has a tension holding it up, and those could be imbalanced, so it's a true static equilibrium. But what about this air hockey puck up here? It's on this frictionless surface, that's why air hockey, right? Frictionless surface. Is this one moving in a circle? Is this in true static equilibrium? No, it can't be. Because Newton's first law of motion says that anything in equilibrium, where all the forces balance, is either at rest or it's moving at constant velocity. That's to say, constant speed and direction. And now this one might have constant speed, but not direction because it's on a curved path. So there is a net force holding it in. That's called centripetal force. And this is what you guys found in your lab last Thursday and Friday before the weekend, was what the relationship was between this swinging mass on a circle of this radial size, fixed radial size, moving at the speed. What's the force that would do that would hold it all in balance? This is almost the same question to switch around and say, like, what speed would it be if you have the other 3 given values? Did anybody solve this by now? Does anybody know the answer? Yeah, I will take you guys through this problem. So I remember from you guys' lab back on Thursday and Friday, you guys figured out that centripetal force, remember, like a center-seeking force, the force that's pulling this puck, holding it in a circle, preventing it from flying off the tangent path, right? It's going to pull it into a circle, is equal to mv squared over r. Right? Remember that was the answer to your lab, mv squared over r, centripetal force? Okay, so the question is, what's the speed? So we're solving for that. As long as you know everything else, you're good. I see a radius, 0.75 meters. I see a swinging mass of 0.25 kilograms. And, guys, what number should I plug in for the centripetal force for this setup? What's the centripetal force? Wait, how much? Well, something. There's some force that's tugging. There's some tension in the string. Hey, isn't the tension in the string being provided by this hanging weight? So is this centripetal force equal to 3 kilograms? Yeah, do we ever measure force in kilograms? No, we always measure force in what? Newtons. Newtons. Okay, how many newtons of weight is this? 30 newtons, right? Because gravity field of about 10 meters per second squared. Right? This centripetal force is being provided by, ultimately, this weight. Maybe I'll do a little subscript 2 to distinguish it from this other mass. Two different masses going on, right? That's actually what's going on, right? Remember that centripetal force is never a lone force unto itself. Centripetal force is always provided by one of the classic forces. It might be a tension in the string, it might be a weight, it might be a normal force, it might be a friction force, but there's one of your classic already known forces is always acting as the centripetal force. And you guys told me that this is 30 newtons because we have a 3 kilogram mass and a gravity field of 10 meters per second squared. It's implied that we're on Earth. Okay? Now the swinging mass that's actually moving in a circle, that's what goes here. So this is 0.25 kilograms. It's in a radial size of 0.75 meters. And well, what is its speed? Well, we're going to solve for that. Okay. Guys good so far? Now, at this step, we are actually finished with the physics, and the rest of this is just algebra. So, say 3 times 10, I'm going to cross multiply up to 0.75 meters and divide down to 0.25 kilograms. So I'm getting v squared is equal to 90. And if you follow the units, you would get meters squared per second squared. Kilograms cancel both, right? And then to get v, just take the square root. And that is 9.49. And the units also get square rooted, which is meters per second. And that's good news because meters per second describes a velocity. Yeah. Or speed in this case, I should say. Constant speed, changing direction. Guys good? You know what I'm wondering is what it would feel like to say, what if you're a fly, you're flying around, you land on that hockey puck, you're wheeling around. Do you think you'd feel like an extra force on you? You guys ever ridden an amusement park ride that might be something like that? Huh. Hey, maybe we could quantify that. So I'm gonna switch over, share screen too. Okay, we're not ready for the cards yet, but here we go. So NASA centrifuge. Right, so this is for astronauts and fighter pilots in training. Well, astronauts in this case, NASA. Suppose you were sitting in one of those boxes, and maybe your back is towards the outside wall, and you're facing in towards the center. If that thing gets speeding up, spinning, would you feel like you're being thrown towards the outside? You would feel like there's a centrifugal force pushing you out. Right? But you guys know from this class that there is no force pushing you outward. What there actually is inertia to the side, tangential to your motion, tangent to your motion, and the back wall is actually holding you in, and that's a centripetal force. You guys know that. Right? I wonder what it would feel like, say, like inside that thing. What does it look like? Let's look inside there. So there we go.
It's ready. I'm ready.
You guys see that G counter in the top left?
Hey, squeeze handbrake.
He's in
Handbrake
1G.
is activated.
You guys are in 1 Earth G, aren't you?
3,
1 Earth
2,
gravity.
1, engage. Legs tight, deep breath. You're on top, breathe. 1, 2, breathe. Drop the shoulders, breathe. 1, 2, breathe. Squeeze your legs, squeeze your butt. Hey, squeeze, keep squeezing, keep squeezing, keep squeezing. Are you there? How you doing? How you doing?
No.
You know what happened?
No, I don't.
Yeah. So you blacked out from G-lock. You guys tell you got it to 9 Gs. Did you guys see 9 Gs? Now you guys are sitting in 1 Earth gravity right now. If you're say like in deep space, it would be 0 Gs. We're sitting in 1 G. He got up to 9. Like his heart was trying to pump blood through his body that was like 9 times as heavy. Yikers. So I wonder. Well, if we're talking about G's, that's sort of an acceleration idea, isn't it? Like 1 Earth gravity, we're talking 10 meters per second squared. That's like an acceleration. I wonder. Say again, if you're like a fly, like landing on this, along for the ride. Say with these exact numbers, I wonder how many G's that would be. And one reason I'm kind of wondering that is because the numbers for this setup actually are pretty close to what you guys had with your lab setup. I mean, your guys' speeds were pretty close to the speed. Your guys' radial sizes were pretty close to this radial size, right? So, what if you had a fly in this top Play-Doh canister? What would that feel like? Well, I know centripetal force is mv squared over r. And I know Newton's second law of motion says that acceleration is a force acting on a mass. So maybe I could take these two ideas and put them together, make some progress. That would mean that centripetal acceleration is just centripetal force divided by this mass, which just works out like this, v squared on r. That's a handy formula right there. Centripetal acceleration, your linear speed squared divided by the radius of curvature that you're on. Right? Now let's run the numbers for our fly friend inside this Play-Doh bucket, this Play-Doh canister up here. So I know how fast it's going because, well, we just figured that out. It's about 9.5 meters per second. Let's do 9.49 meters per second. Got to square that value and divide by this radius of curvature, 0.75 meters. I wonder how many, we're going to get this in meters per second squared first. 9.49 squared divided by 0.75. That is, look at that, 120 meters per second squared. 120 meters per second squared. Okay, that's in our classic metric units. How many Earth Gs does that represent? Anyway, you guys know you're in 1 Earth G right now, right? Which is how many meters per second squared? 10. Hey, do you think this is like a conversion? Like 60 seconds in a minute? You think we could do some dimensional analysis? Right? So, you guys just told me every 10 meters per second squared is 1 Earth G. I bet you see it now. You guys see it now? How many G's is that? 12. 12 Earth G's. The video you guys just saw went up to 9. So, yeah, 12, that's a little bit more than that, but not much more. So, yeah, if you're a fly along for the ride in your Play-Doh canister from Thursday, that's about what you'd feel like. Let's look at some other centripetal force examples. I have a cup here. Yay, a cup. Last time I had a cup, I filled it with water. That was pretty exciting. So, yeah, I'll do the same thing. Let's fill this with water. Get it nice and full. Yeah. Making me thirsty. Hey, do you guys think there's a way I could turn this cup upside down and not get my room wet? Probably so, because we made it to the end of the day and our room's still pretty dry. Turn the camera. Make sure this is focused here. And move some stuff around. Whoops, I'm still sharing my screen. Hold on. Swap that. Okay. If you're at home watching this video, do a close-up of all that math we just did. You screenshot that. All right, there you go. All right, move this around. Okay. So I got this cup of water. And hey, what if I spin this in a circle? Let's go this way with this thing. If I spin this in a circle, is water going to stay in the cup? Let's find out. Whoa! Oh, water's staying in. Do you guys think maybe there's like a minimum speed just to barely get around? Like if I do this too slow, I think the water's probably going to fall out. Do you think we could solve for that minimum speed? Let's try that out. Let's see if we can solve for the minimum speed to keep this water in this cup. Now you guys know centripetal forces work. Clear this table right here. Well, I'm thinking that the place where the water was most vulnerable to fall out was right when it was at the top. So let's go to that point. Where the cup is upside down, the water is there. And well, you guys saw some strings this cup was on. This cup was following a curved path. And the radius of the path was right here. Called R. Maybe there was some mass to this. You know what could be helpful too? Maybe is if you anthropomorphize this by putting a little goldfish. So I got a little goldfish swimming around inside that water. Imagine you're along for the ride. Hey, if this is spinning around with, let's say, sufficient speed, like the water's not in danger at all of falling out, so sufficient speed to get around, so this V. If it's going around faster and faster, do you think this fish feels like there's a centrifugal force throwing it upwards toward the bottom of the cup? That's what the fish thinks is going on. Right? Now that's from the fish's frame of reference, like a rotating frame of reference. But from our frame of reference, an inertial frame of reference, is there any force that's upward on the fish? No, there's no upward force. What there is there's inertia making the fish go to the side. So I could cut this right here. Won't the whole cup go left to the side? And also there's the bottom of the cup that's holding the water and the fish in place. But there's no upward force on the fish. Right? Okay, how about a free body diagram? What are the forces on this fish? Well, I know this fish, or the water for that matter, has a weight. Whether you want to think of this mass, talking about the fish or the water, it's up to you. In that weight, we call that mg, the weight. Now, usually, if there's sufficient speed to get around, isn't there also additionally a normal force from the bottom of the cup holding even more? Right. That is true. Right. But here's where we're going to actually answer this question: is I want to figure out the minimum speed just to get around. So throw a little subscript on it, v, call it minimum. Right. Here's the question: what is v min, like the minimum speed to get around the circle? Maybe we could phrase that different, but I like that, right? So the water doesn't fall out. Well, here's what I know. I know the centripetal force, this has something to do with that, is mv squared over r. So got that. Well, maybe I should give you some values. I don't know. I'll plug in the numbers later. And centripetal force, remember, is always provided by one of the classic forces. Hey, in this case, couldn't it just be the weight? Right? Like if there's no other force, if the fish is just barely getting around, I'll tell you what the fish would feel like if it just barely gets around at the minimum. Wouldn't it feel like it's an astronaut just for one instant? Like it would feel weightless, kind of like you jump off a ledge. There's a force on it that's just kind of in free fall just for one moment. So this, what I'm trying to say is that this right here is represented by the weight of the water or the fish, mv squared on r. We're solving for v, and this would be the minimum speed in the case that the force was only represented by the weight, nothing else. Okay. What's gonna cancel out? The mass. That's to say the mass of the water, the mass of the fish. So if I went back and I added more water to the cup, does the answer to this problem change? No. Well, as long as that doesn't affect the radial size, right? Notice I'm going to the center mass of the water. So as long as that doesn't change, then yeah, the minimum speed doesn't change either. Cross multiply the r, so v minimum squared is equal to gr, and then take the square root for gr. Well, that's a general expression, but how about for the numbers that I gave you? Or you know what? I didn't even give you any numbers. So let's make up some numbers. So gravity, we'll call it 10 meters per second squared, because that would be Earth gravity. Okay. And notice the mass cancel out, so you don't even have to, you don't care about what the mass is, just make up whatever. But radial size, let's get an actual radial size on this cup. Pour off that water. Let's just see, what was the radial size of this thing? All right, so if I let meter stick go to the center mass of the cup, where the center mass of where the water would be, it goes to pretty much exactly, I'll show you guys here, about 50 centimeters, like almost exactly 50 centimeters. Okay, so that is the radius of that circle, 50 centimeters. So wouldn't that be 0.50 meters? Remember, going from centimeters to meters, 100 cents in a dollar, that's 2 decimal places. See what that would be. What is the square root of 10 times 0.5? That is 2.24 meters per second. There you go. So if you swing it around and it's going that speed right at the top, it's just barely getting around, and that fish would feel weightless. If it's going any slower, the water's going to fall out. And if it's going any faster, then everybody's safe. That's all good. This problem's going to come back a few weeks from now. when you guys are solving a very similar problem, let's say like something about a roller coaster going through a loop, and I bet it has to have like some minimum speed to get around the loop, and maybe that's related to some other things we're going to study in the future too. You guys good there? Oh, I want to do 2 more centripetal force type problems, and then we'll move on to other stuff like universal gravitation. So let's talk about a flat road, and let's say a flat curved road. So what is the max for a car going around a curve on a flat road? When I say flat, I mean horizontal, like there's no bank. There's no bank to it. We'll look at the banked road too. That'll be the last thing we'll do. So I've got a road, goes into a curve, something like this. We're up on a helicopter. We're looking down. We see this road. Oh, you know what? I didn't even realize this all day, but so maybe it makes more sense as a solid line. I think dash means everybody's going the same direction. Whatever. So we got a car. We're looking down at this car, and the curve part. Notice that it starts out straight here, but the car is on this curvy part. This curvy part is it's associated with some radius of curvature. So I could draw a circle right there. Okay? So here's R, radial size of that circle. Okay? This car is going at some speed, call it V. Okay? Notice how V and R are perpendicular to each other, or well, I tried to draw it that way. Pretty close. Okay. That R and that V are perpendicular, I said. Maybe this car has some mass. It should make up numbers for these. I'll give you a radius of curvature of, let's say 100 meters even. Okay. Let's say the mass of your car is like 1,900 kilograms. And you're trying to solve for V max. Like if the car's going too fast, it's going to like slide off the road. Okay. If the car does go too fast and slide off the road, which way does it go? Does it go forward in the direction of its motion, or is it going to fly off away from the center of the circle? What do you guys think? If the car slips and starts sliding, how do you guys say it's going to go forward in its direction of motion? Yeah, because that's what Newton's first law of motion says. That's exactly it. Okay. Speaking of which, what force is actually allowing the car to make that turn? Because remember, the road is flat. The road's not even banked. If it was banked, then it could just be something to do with normal force. But if it's a flat road, what force? Friction. So you know what? You need another number that I haven't put on here yet. What's the other number that you need? The coefficient of friction. Okay. So I'll give you guys a coefficient of static friction of 0.85. See that? Now there's enough information to figure out what's the maximum speed you can go. You guys ever, I'm sure, left the interstate, you're going around that curve, and it says has some speed limit on there, and if you're going too fast, it goes like, ooh, like this car's about to like topple over or slide off. Okay. Pretty similar to what we're looking at here. Okay. Well, I know that I'm going to do a bunch of substitutions over here. Okay. So I know centripetal force is mv squared on r. Okay. You guys know that from Thursday, Friday. Okay. I know centripetal force is always provided by some classic force. In this case, it is friction between the tires on the road. So I'll say friction force is equal to, that's what's providing your mv squared on r. Solve for the speed. Okay. And friction, you guys remember from last couple of weeks, friction is equal to what times what? Coefficient of friction times normal force. Okay. We're looking at static friction because we're trying to max out the speed of this car. So that would be static in that case. You can still say equals. Right? And, if the road is flat, which it is, that's part of the premise. What is the normal force also equivalent to? The weight of the car. Now, I'm not drawing that for you by a diagram because that would go into and out of the paper. You have to think in 3 dimensions. The weight of the car is down, the normal force is up. But those are balanced out, aren't they? So I can say, this is mg, so coefficient of friction times mg is what's providing the centripetal force for that car to stay on that circular path. Okay. Ooh, what cancels out on both sides? The mass of the car. So if you went to the grocery store, you loaded up that car with groceries, and you make a return trip, is the answer to this question of how fast can a car go, does that change? No, makes no difference. Right? Mass cancels out. Right? Let's solve this in terms of variables, because it's 2 steps away anyway, right? Just multiply the r and take the square root. So V max, which we'll solve for, you have 2 steps. Multiply r, take the square root. So square root of mu g r. That's a general answer. Let's plug in some numbers. Coefficient of friction, I made up this number, 0.85. Gravity could be 10 meters per second squared. Ooh, so if you changed planets, would the answer change? If you changed planets? Yes, it would, because that's part of this. Right? So maybe the same road would not work on Mars. Right? The radial size I gave you is 100 meters. Check this out. I wonder what this comes out to. It's 0.85, 10, 100 meters, square root of all that. Looking at Vmax of 29.2 meters per second. So if you're going 29.2 meters per second, see what that actually is. That is about 65 miles an hour. Ooh, so talking about highway speed, you would be right at the breaking point where the tires are about to slip from the road. Go 30 miles an hour, you are out of luck. And one more centripetal force example. Let me share screen 2. Hey, it's our old friend. But I'm looking for, oops, not that folder. Where's, cars on a wall. All right, I'm gonna mute that lovely sound. And, ooh, I see some motorcycles on a very steep banked wall. Okay, so this is a banked wall now, right, in contrast to what we were just looking at, banked wall. I see some motorcycles and dynamic equilibrium. Remember, it's not true static equilibrium. There is a net force on them. It's holding them in a circle. But that circle size isn't changing, and they aren't drifting up the wall or down the wall. So I wonder what speed that is, or what it has to do with other physics variables. Hey, look at those cars. Do you think those cars are going to go up there? Yeah, those cars have much greater mass than the motorcycles, don't they? Much greater mass. And if that's true, then should those cars go faster, slower, or the same speed as the motorcycles to also stay in a circle of constant size? Let's just show of hands what you guys are thinking. How many of you guys think those cars have to go slower than the motorcycles? Who says slower? Who says faster? And who says the same speed as the motorcycles, the mass is going to cancel? Yeah, there's my winners right there. Yeah, so mass ends up canceling in this question. So the dynamic equilibrium speed for constant size circle does not depend on the mass of the vehicle. Right? Depends on other things. Depends on radius of curvature. Depends on the how steep that bank is. There you go. Got that. So let's solve this thing. So let's see, stop sharing my screen. Gonna flip back. Actually, I'm not gonna even solve this whole thing with you. I will show you the setup for it, and we may or may not come back to this later. Probably not, but at least show you how to set this up. So, car on banked wall. So let's draw a big old banked wall here. This is at, you guys saw a really steep angle. I know maybe it was like 60 or 70 degrees, just some crazy steep angle. Park a car up here. Now our point of view is we're behind the car, we're looking at its taillights. Here's the back windshield. And this car is going into the paper and around a curve. So it's going into the paper, going around like this. At some speed v. So draw a little bit more. So here's the curve going around like what you guys just saw. Something like that, right? Good so far? All right, now I know that if this car speeds up, it's going to tend to drift up the incline. If it slows down, it's going to kind of tend to drift down. I wonder what the forces look like to hold this car in balance. Well, this car better have a weight. I mean, if there's no weight, there's really not a lot of excitement going on. So MG, pulling straight down. That's your MG. I forgot to mention a small detail. That's no friction. Suppose it's like iced over or something, or maybe there is a little friction, but it's not needed to hold the car in one circle size. So we're going to ignore friction. There's one other force on that car. So its weight's pulling down. What's the only one other force? What force from the surface of an incline? The starts with an N? Normal, the normal force. Normal force is perpendicular to that surface. Just about like this. Oh, I should ask you guys too. I'm going to throw this up and ask guys. What force do you think has a greater magnitude? The weight down or the normal force up to the left? Well, they would be the same on a flat surface, but if it's an inclined surface, they're different. And usually for what we've been looking at, usually the normal force is less than the weight. In this case, it's going to be more. I'll show you guys why it's more. So this is the normal force. Because if you split this into components, you say, well, that normal force is partly holding the car up and partly pushing the car in. Think about what each of those components mean. The upper part, hey, doesn't the upper part have to exactly balance the downward part? So the normal force is both holding the car up, but also holding the car in a circle, like providing the centripetal force. You see? So this, I have to label this angle. This angle is theta right here. Here's your normal force times cosine of that angle. That's equivalent to the weight of the car. And what about this other component? So this would be the sine component of the normal force, and that's equivalent to the centripetal force. Where I told you guys normal force is much greater magnitude than the weight of the car. That's how this works out. Okay. That's the setup. You can go solve for, well, the question would probably be, what is this V? What's the speed of the car in order to also stuff? Let me put the mass on here. Or not the mass, the radial size. Mass is going to end up canceling out. You guys know that because you just saw that. Here is the radial size. Call this R. Okay, there you go. And if you know theta, R, and also gravity, you can go solve for G or V. Okay, good. So that's the setup. Okay. Right, get ready to move on to universal gravitation. And so we're going to put this to the side. It's going to come back when we're doing orbits. Let's talk about universal gravitation. Because we talked about weight as a force in this class quite a bit. But you know what? I never told you exactly where it comes from. Like, you know that if you're on the moon, you weigh less. You know, if you're on a bigger planet, you might weigh more. But so the mass and radial size of the planet has something to do with it. We're going to get two bodies floating around in space. This might be two asteroids. Hey, maybe this is like a planet and the moon. Maybe it's that. Maybe it's a planet and the moon. So I'll call the planet mass big M and the moon mass little m for the masses. And these are separated by some center to center distance, R. There's your center to center distance. Notice I'm going from the center mass of one to the center mass of the other. Okay. And there's a gravitational force from one to the other. So the planet is pulling its moon to the left, and the moon is pulling its planet back to the right. Now, you guys know which of those forces is actually the bigger force. What do you guys say? They're the same. Yeah, it's Newton's third law of motion. It's the same force. Okay, all right, so can't trick you guys again. So what is the magnitude of that force? Well, it goes like this. We're going to multiply the two masses together, so the force is proportional to each mass. They leave a little space here, so m times m. I'm going to divide by the center to center distance between them squared. Now, it should make sense why you divide by the distance, because the further away you get from something, the less the force, right? Makes sense. If they're really far away from each other, it'd be very little gravity force. But why squared? Why is it inverse square law? Why not just hit inverse? Why inverse squared? I'll tell you guys that in a few minutes. But one more thing. I'm going to throw in this letter right here, capital G. This is the first time you guys have seen this in this class, at least on the notes. And G stands for universal gravity constant. Okay. And as far as physicists know, it appears to be the same everywhere in the universe. Nobody knows why or why it is what it is, but they have measured it. It's been measured to be this number. Very tiny number. Of the four fundamental forces, gravity is considered to be the weakest of those. Remember, there's gravity, there's electromagnetism. Those are the ones we care about in this class. There are a couple of nuclear forces, strong force, weak force. There's probably at least another one out there, like recent science. Right? And actually, if you want to get strict about it, get to upper level physics, gravity ends up not being a force. It's an artifact of the curvature of space-time, and this is only an approximation. But for this class, we'll call this a force. Work out these numbers. And this number is so small, this universal gravity constant. Well, hey, you know what's about to come back? Scientific notation. Can you guys write that as scientific notation? 6.67 times 10 to the minus 11. 8 meters squared per kilogram squared. Scientific notation is definitely making it back this week because there's not only this very small number, some of these numbers are very large numbers, like the masses of planets and eventually stars. Right? Is that? Yeah.
At the end, the unit of measurement, what is that?
Oh, Newton meter squared per kilogram squared?
Okay.
Oh, yeah. There you go. Newton meter squared per kilogram squared. And then if you plug it in, then this whole thing works out with some number of newtons for the force. All right, so 2 questions. One, how is this even measured experimentally? And the second question is, why is this divided by r squared? So let's do this one at a time. How could you measure what the universal gravity constant is? Well, here's one way to do it. You got a couple of scales. Scale, scale. Gonna balance these things. Do something about like that. Throw a little lab weight here. Some value little m. Do the exact same lab weight over here. Same value little m. Doesn't everything balance? Okay, so everything's balanced, everything's good. Until you do this, you throw a big old mass, I'll call this capital M, big old mass underneath one of the lab weights. Let's say it's sufficiently far away from the other one. It doesn't really affect it, but it's close to this one. How close? Well, some distance, center distance r. Well, that value r. And by having it there, isn't it going to be a little gravity tug? It's going to throw off this balance just a little bit. So then what you can do is you can take another lab weight of known weight. I'm talking about tiny, and that will pop it over here. That's going to restore the force. And if you know what this force is, this force F, then you can say that force, this one right here, equals Gmm over r squared, where you know this m, you know this m, little m, you know this r, and you can back solve for that g. That's why you can experimentally do that. Okay. And that's how they know if that number is that number. Again, nobody knows why universal gravity constant is 6.67 times 10 to the minus 11 newton meters squared per kilogram squared. It's just been measured to be that value. And the other question was, well, why is there an inverse square relationship between distance and force? Like, I get inverse, you're further away, there's less force, but why inverse square? So, I'm going to give you guys a candle analogy. So, inverse square law. Let's do a candle analogy. Because light also works the same way as gravity works, same way as electrostatic force works. They all follow this inverse square law. So let's get a candle. This candle flame is putting out light in all directions, equally, spreading light in all directions. Let's focus on one particular cone of light. So I have a dashed horizontal line. Some of this light's going up this way. Some of this light's coming down this way. I've got like a cone of light. I see it. And maybe I want to know, as I get further and further away, how is that light dissipating? Like if I'm really close to it, it appears really intense. And if I'm really far away, it's really dim. So let's mark out some different distances. Maybe I want to go 5 centimeters away, and then 10 centimeters, and then 15 centimeters. Now I'll call those distances R, 2R, and 3R. 2R and 3R. Okay, got those distances. Now if it's a cone of light, then the amount of light on this cone would, of course, cross-section would be a circle. I'm going to simplify that a bit and turn this into like a square type shape. Okay? Let's say I got a square at the side. If I have a square, that might look something kind of like this. Okay, so you guys see that square in 3 dimensions? It's turned about like that. Okay, that's capturing all the light from the candle, isn't it? Okay. Let's back up to twice the original distance. So we're going twice as far away and set up a similar type square. Okay, does this square look like it's twice as tall as the original square? You guys see it's twice as tall? Okay. So, but don't forget that also it's going twice as far back into the board, twice as far back into the paper. I see that too. Okay. So now the same size original square. You guys see that hashed in square is the same original size as the original one? Well, it's supposed to be pretty close. Okay. You guys see it's only catching 1/4 of the light? 1/4? Ooh, so it's looking like the amount of light that you capture per some unit area is proportional to 1 over the distance squared. Because you have twice the distance, you only capture 1/4 of the light. Let's see if that pattern holds for 3 times the distance. So now I'm going to go to 3 times this distance. So right now, paper up here, but like this. Ah, look at that. So here's the original size square again, but you guys see that that's only 1/9 of the total now. Okay. So same size, but this one's 1/4 of the original, this one's 1/9. Okay, so there's an inverse square relationship between your distance and how much light you're touching. You see that? Okay. So light works that way, electrostatic force works that way, and so does gravity. So as long as you're living in like 3 spatial dimensions, you tend to see this type of relationship. Okay, let's take this back down to a planet and some more ideas. So back down on the planet, has some mass m. You're standing on the surface. You have mass little m. Okay. And where's your actual weight coming from? Well, it is this formula. F equals g m over r squared. Okay. I'm going to change the r to a capital R. Sometimes I do that if there's like a fixed radial size, like the radial size of a planet. We'll do that here. Okay. This force now represents your weight. Okay. And, yeah, sort of a new formula, but not really, because that's really the same thing as we just looked at. Okay. Now, how does this translate exactly? I mean, I get the G in the little m, okay. But how about these other things? Why can the mass of the planet be treated as a single point mass right at the center? And that's exactly what we're doing. You guys see how we're treating the entire planet's mass as if it's a single point mass right at the middle? Okay. A little bit of simplifying assumption. The planet is actually like spread out over its entire volume. Some of it's a little bit to your right, some a little bit to your left. That definitely cancels out. Some a little closer, some a little further away. The net effect is we're going to say that it's as if the distance between you and the planet is also the radius of the planet. Okay? You guys good with that? Okay. But there's something else I want to do with this. I remember Newton's second law of motion. It says that acceleration is a force acting on a mass. And this is Newton's second law of motion. Okay? And if you took this original force and you divide it through by any mass on the surface. This could be you jumping up and down. This might be Galileo dropping stuff off the Leaning Tower of Pisa. Do you think that everything's going to free fall at the same acceleration? You guys know it does because you did this in your lab, and it's one of these stories that keeps coming up in this class. How is that going to be consistent with this? Well, if you divide through by any surface mass, you'll get the free fall gravity of the planet is G, universal gravity constant, times the mass of that planet divided by the radial size of that planet squared. Now you guys have a way to solve for the free fall gravity of the surface of any planet. Hey, look at that. And the last thing we're going to do today is plug in the numbers for Earth. So got 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared for this capital G. The mass of Earth is 5.98 times 10 to the 24 kilograms. The radial size of Earth is, make sure I got this right. Yeah, 6.38, 6.378 times 10 to the 6 meters. Don't forget to square that. Okay, good so far? Yeah, plug this in the calculator, see what happens. 6.67 times 10 to the minus 11, this is your universal gravity constant. I got the mass of Earth, 5.98 times 10 to the 24 kilograms. I'll divide it by open parenthesis. 6.378 times 10 to the power 6 meters, close square. Okay? Now, when I hit enter, you guys know the number that's going to pop up on my screen. What's it going to be?
Well, more specifically, 9.7?
Yeah, something like that. Yeah.
9.7.
Look at that right there. 9.8 meters per second squared. Oh, yeah. And that is our pause point today.